Assalamu alaikum everyone. So lecture number 14, and we will resume our last review and recap portion. So these are the two topics which we already have gone through, and rest of the topics we will be touching upon while having review questions, and then we will try to have a recap quickly, right? And the topics are protocols, what is protocol data unit, PDU, and then we will be talking about the protocol architecture. We will be having some question from TCP/IP stack, and then we will discuss about the advantages of following the layered approach when we are defining the protocol, then the router, its functionality, and its architecture. So we will be having review questions from those topics, and we will be recapping them quickly while solving those review questions. So let's start. So first, what is a protocol? So let me give you a very simple example that two ambassadors from two different countries, they have to arrange a dialogue between two countries. So what normally they do before having the dialogue session or the actual session, they define some sort of set of rules and regulations. What are the issues we will be talking about, and if their native languages, they are different, so they have to arrange a translator, and if they have to sign some agreements, so there are certain set of rules and regulations by following which they will be signing the agreements, and so on and so forth. So they have to define certain rules and regulations before starting the actual dialogue. So that's what defines a protocol, right? So we can define protocol, a set of rules that govern all the aspects of data communication between endpoints, between devices, between the equipment that is actually used in order to construct the network, right? So what are these rules? So these rules, they actually guide or regulate the characteristics of a network. For example, how the endpoints or the computers or the devices, they will be accessing the network media. Then how they will be connected with each other, that is related to topology, right? And we can also define certain set of cabling mechanisms, methodologies, and this is very important, the speed of data, right? For example, if one endpoint, it has a capability of 1 megabit per second, and there is another endpoint or computer that is lying within the same network, but it has the capability of 2 megabit per second. So whenever they are actually going to start the communication, so they have to define that what are their capabilities and how they are going to send data, and obviously if 2 megabit per second capability computer is sending data to 1 megabit per second capability computer, so the 2 megabit per second capability computer have to segment the data, right? Because the other endpoint, it don't have the capability or it don't have the the interface that can accommodate. So all has to be defined when we are going to start the actual communications, right? So we can also have a very precise definition of a protocol that actually defines what, how, and when it has to be communicated, what has to be communicated, and how they will be going to communicate, and when. Timing is also very important. So some of the key elements of the protocol are the syntax, then semantics, and timing, right? Okay, So these are the key elements of the protocol: syntax, the structure or the format of the data, how they are going to represent the data. So it has to be defined so that the two parties which are going to communicate with each other, they can understand the data correctly and exactly. So they have to define the structure or format of the data. Then semantics. So you have defined the format of the data, but the endpoints should also be able to understand the meaning of the data, right? Because if we talk about the computer communication, so they are going to send bits to each other. So each bit or set of bits, they have its own meaning. So the corresponding parties which are involved in the communication, they should be able to understand the meaning of the bit. For example, if they are sending a 4-bit flag or exchanging a 4-bit flag, and they should be able to understand that what does this flag mean, right? And then obviously if they are sending a certain pattern of bits, so it has to be interpreted, it has to be understandable. So the example of the semantics is, does an address identify the route to be taken? This is one example, or the final address of the message. So maybe it's the address for further routing, or maybe this is the final destination. Then timing is very important when we talk about the protocol. When data has to be sent and how fast it can be sent, because timing is obviously correlated with the speed of the data, because if we say 1 megabit per second, so it's mean the unit which we are defining is second. And then each packet on the internet, it has its own life, time to live, TTL. So there is a flag that is associated with each packet. So again here the timing is important. So and then when we talk about the transmission, so when data has to be sent. So these are the timing elements. So we can take the example, if a sender, it have the capability of 100 megabit per second, but the receiver on the other side, it can receive only 1 megabit per second. So it means the transmission will be overloaded, and the receiver overload the receiver, and the data will be largely lost. But so that's why we have to take care of the timing. So obviously we have to chunk down the data into smaller chunks, and then we will be sending. Then we have certain characteristics of the protocol, or you can say certain properties or capabilities. For example, direct, indirect communication between two end parties, between 2 points, 2 entities, maybe direct or indirect. So there can be intermediary devices that are actually involved. So our protocol should have the support so that it can have the capability, or it provide the capability of direct or indirect communication. For example, if we have routers, switches, and some other devices, whenever we have to transmit data from one endpoint to another endpoint, so the protocol should support that those underlying interconnecting equipments should be facilitating or complementing the communication. Then point-to-point link, P2P link. So connection, this type of sort of connection provides a dedicated link between two devices. So in this mode, maybe we have more than one choices, but whenever we talk about the P2P link, so it is a dedicated link between two devices and entities. Then multi-point link. So this type of connection and in that mode we have more than 2 devices that can share a single link. So here we have the sharing. So you can see point to point, right? So these are the examples: workstation, mainframe, and then we can also have the example of satellite communication where we have the point to point link configurations. So these are some of the examples regarding the protocols, and they are being used currently by different devices. Point to point, used to manage network communication over a modem, and then transmission control protocol, TCP/IP. So this is actually the backbone protocol. Whenever we talk about the internet network of networks, so it has a huge backbone. So TCP or IP, it support the it is being used in the backbone that is actually complementing the communication over the internet. Then Inter-Network Package Exchange, IPX, and NetBIOS, FTP, used for the sending and receiving files. SMTP, Simple Mail Transfer Protocol, used to send email over a network. So you can say that's a store and forward sort of protocol, because whenever we send an email to a destination or to an email address, so that email is stored over the server, and then it is delivered to the underlying address. So it's SMTP. Hypertext Transfer Protocol, HTTP. So it's very popular protocol over the internet, used to send documents encoded in HTML, a language. Then Apple Talk, OZ model, OZ layers. So here we have, after discussion about the protocol, actually it's a set of rules in order to govern communication or manage or handle communication between the endpoints. So there can be different type of protocols. So for example, let me give you the example of a phone call, right? So whenever we have to make a phone call, so first there is a call setup. So there is a unique protocol that is used in order to have the call setup. In case of voice over IP, we use SIP in order to make a dialogue between the end parties, right? So that is regarding the voice over IP. And regarding the previous example of a phone call from a cellular phone, so there are a lot of different choices depending upon the technology which you are using. So you have to use a signaling protocol in order to set up the call. So after setting up the call, the actual data starts flowing. So in that case, we will be using a codec, right? Or you can say another protocol, and in order to have the actual data starts flowing. So we have different type of protocols for different purposes. For example, we can have a specific protocol in order to transfer files between endpoints, and then we can also have another protocol in order to access the web pages, for example HTTP over the internet. So there are some important elements of the protocol, and these elements are syntax, semantics, and timing. So these are the important elements, and they define that what, when, and how the data is being transferred between the end parties, between the corresponding parties. So after the discussion, we have the answer of our review question. A protocol is the set of rules or conventions governing the way in which two entities cooperate to exchange data. So this cooperate actually is the setup or signaling, you can say. So next review question, what is a protocol data unit? So as we have different layers and the functionality over those different layers, it has already been decided or predefined. So they add their own data. So what is normally going on, for example, if we talk about the OZ model, we have the application layer at the top, and then we have the presentation and session and transport, right? And then after the transport we have network, and after network we have the data link and physical, right? So we have 7 layers: application, presentation, session, and then transport, and then network, and after the network we have the data link, and after the link we have the physical layer. So all those layers, they have their own functionality, and as a result they are actually adding their own headers, their own control information. So if I start from the application, so application layer has its own, for example, some user application, and we have the original data that has to be transmitted. So the application layer will add its own header, and we have the data or the actual message that has to be transmitted or transferred by using some of the protocol. Then the data, actual data, plus the control information at the application layer, that is enveloped, and it is sent to the next layer, that is the presentation, right? And then presentation layer will add its own header, right? And it will take the data plus header from the application layer and as the original data, and then will add its own header, and then they will deliver the underlying data to the next layer, session layer, right? So now the session layer will take all the headers from the application and the presentation layer plus data as data, and then it will add its own header. So this will continue till we will reach at the physical layer. Let's talk about where PDU lies within that mechanism, right? So at each layer, protocols are used to communicate. So as we know that there can be different set of protocols at each layer. So every layer adds its own control information, right, to the user data, that is the actual data. So PDU is then defined as the data, that is the actual data, plus the control, right? So you can say that PDU will be control data plus the actual data, right? So as I mentioned there, you should be very careful that when we move from one layer to the other layer, right, if I'm talking from the sender perspective, right, so the data coming from the upper layer will be taken, data plus control information coming from the upper layer is taken as the data, right? And then the next layer will be adding its own control information, right? And then if we talk about the receiver, so those headers are being used and exploited accordingly at the corresponding layers. That the presentation layer at the sender, right, it has its effect on the presentation layer at the receiver, right? So we have the example: transport layer may fragment user data. Each fragment has a transport header added, of course. So destination port, sequence number, error detection code. So this gives a transport protocol data unit, right? So here we have the application data, right? So you can see that at the transport layer, the data is segmented, right? So this is the segmentation. So this is the application data, right? It's segmented, and it's the transport layer is adding its own transport header. So here again, so you can also have the segmentation identifier over here, and then that data is actually sent to the network layer, and network layer is adding its own header. So you can see, you can watch that this whole data plus control information at transport layer is taken as data over the next layer at the network layer. So network layer will be adding its own header, and so on and so forth. So network PDU adds a network header, network address for destination, computer, and facilities in order to have the complementation. So now we have the answer of our review question. What is a protocol data unit? So is the combination of data plus the next higher communications layer and the control information. So segmentation, actual data, segmentation of actual data plus control information, and that is actually the data for next layer. Then next layer will be adding its own header, right? So you can say that this is the PDU for the next layer. So protocol architecture. What is our protocol architecture? So first we have to establish that why we need the protocol architecture. So there are a lot of different applications that we can say that are actually natively developed for networks. So it's very difficult to build each application from the scratch, right? So there are certain problems if we do so, that we sit and we start developing every application from scratch, from zero, right? So there are some of the cons. So what commands should be supported, how to respond to each command, what is the action, what are the actions that has to be taken as a result of that command, how to identify the two-peer applications. Each computer may run multiple applications, so there can be multiple applications that are running on a single machine. So how you can identify two different computers, and how to convert the data into bit stream. We have the data, and obviously when we want to transmit that data, or when over the network, so we have to convert that data into the bit stream. And then of course whenever we talk about the data within a computer, so we actually are playing with bits, and when we have to transmit that data over some media, for example copper wire or coaxial cable or maybe fiber optics, so we have to convert those bits into signals. So data representation, and how to detect and handle if we come across errors, right? So in order to answer all those questions, right, so we need to have a protocol architecture, right? So actually there can be another justification that and this has been discussed before when we were talking about the network communication, that the communication, especially the data communication between endpoints, it's a very complex task, right? And we don't want to perform the complex task again and again starting from scratch. So there can be a lot of problems, a lot of overheads. So in order to make the life easier, what we did, what we do, we divide that complex task into smaller subtasks, and we assign those subtasks to different layers. Now each layer knows its functionality, and we can define different protocols, we can define different applications, and we can also develop different equipment that is going to complement or support the functionality at the corresponding layer. So better if tasks broken into subtasks, implemented separately in layers in stack, and then in order to have communication between peer layers, we can define certain set of protocols. So this is the same. So this is an example. So when we talk about the network communication, so there are certain network applications, there are certain modules, intermediate devices, right? Those are involved in order to enable or complement the communication, data communication between different parties, right? So there are chances that some of the network applications, they are sharing some common modules. So here we have shown that these are the common modules. So this is the same, that we have to chunk down the complicated task of communication, underlying communication, into subtasks. So modular design. So you can say that each layer is representing a modular design. That is in the vertical stack, and you can have a vertical stack when we talk about the subtasks. Each layer performs a related subtask or functions, and this is about the communication between the corresponding or peer layers, services to the next higher layer. So maybe it is providing some service to the next higher layer. Layers should be defined that the changes in one layer do not require changes in the other. So this is very important, that if I'm the person who is related to the network layer, and I have to think about the routing protocols, routing the intermediate devices that perform routing. So if I want to make the change, so I have to I know my limitations. So as a result, I will be following or complying all those limitations. I will be developing or defining or building the corresponding functionalities by keeping myself within those limits, and as a result the other layers, they will not be affected. So there is not any change that is going to be required if I'm going to change some of the functionalities or some of the tasks, subtasks that has been performed at the network layer. So this is another advantage. So as a result, what we can have, instead of using a very complicated protocol, we can have small protocols, and that bunch of small protocols actually build up the protocol stack, and we can have a very flexible sort of intercommunication between different devices, right? So here we have a vertical stack. So you can see that different tasks, they are defining actually modules at different layers. So those modules, they are actually important for the operating system, and then above the operating system, over that operating system, the application developers, they have to develop different applications, so they know their limitations, their pros and cons, and the operating system is actually residing at those different modules, or it's communicating with those different modules. And then here we have the hardware, right? So you can see that these modules or these subtasks, they are actually relevant to the hardware. So we can have a very simple example. A can only speak Chinese language, B can only speak Spanish. So how they can communicate with each other? So A finds a translator, C, who can speak Chinese and English, and then B finds a translator who can speak Spanish and English. So you can see that though we can have a person who can speak Chinese and Spanish, right? So here we have two-step communication. First, the Chinese person will speak the Chinese, and it will be translated into English, and then the person who knows the English and Spanish, he will be translating that into Spanish, and the Spanish, because the ultimate goal is to have communication between Chinese and the Spanish person, right? So as a result, after the 2 hops, job is done, right? 2 layer, higher layer A and B, and lower layer C and D. So here you can have an idea of the layer, right? So A will be communicating to the B, right? And then C and D. So actual message has to be communicated between Chinese and the Spanish. So here we have the protocol architecture. So as we have mentioned here, that we have to send messages between 2 people, and they have different languages, so we have 2-hop communication or 2-step communication, 2-layer communication. So here tasks of communication are broken up into modules. Each module have its own protocol. So as there are certain set of rules, you know, every language has its set of rules, so they have to follow those rules. So each layer has its own protocols in order to be able to understand the messages communicated between 2 end parties. So as mentioned, the task of communication is chunked down into smaller subtasks. So if we have different tasks and we define different modules, right? So each module or layer can have its own protocol. As you can see in this example, we have set of protocols or rules for each module. Communication can be said to involve 3 entities: computer applications at the top, and then computers, those are the endpoints going to be communicating with each other, and then we have the intermediary devices that are actually building the network or complementing the communication between the end parties. So applications, computers, and networks. And we can take the example of the file transfer, and it can use 3 modules or layers: file transfer application at the top, and then the communication services modules that are being involved in order to make sure the error-free file transfer, and then the network access modules, right? And the stack of protocol is called protocol stack or protocol architecture. So let's talk about the TCP/IP protocol architecture. So that was actually developed by US Department of Defense, and it is used by ARPANET. So now it's very popular protocol that is being used over the internet. So it's actually a bunch of protocols. Each layer has different set of protocols, and that's why we can say it's a stack of protocols. So each protocol is performing some task, some subtask, some functionality. So you can also read, if you are interested more, at this link, in Internet Engineering Task 4. It's an RFC, standard RFC. So in literature, the top 3 layers, they are almost the same, but the bottom 2 layers, in some literature, they are merged together, and in some other literature, they are presented at distinct layers, physical and the network layer. Okay, so here we have the example. For example, we are actually using the World Wide Web, and that is in order to have this application functioning, we are actually relying on the HTTP protocol, Hypertext Transfer Protocol. So it's a web browser that or web application, right? So that is World Wide Web. And then at the top layer, the browser should be capable of handling or understanding or receiving or sending the data via HTTP, and then at the lower layer TCP, that is encapsulated and sent as TCP, and then at TCP layer the data is fragmented because now we have to send the data, and we are using actually IP addresses in order to send the data. So segmentation, and different segments are sent to the IP layer, and IP layer will be performing more smaller segmentation, right? And we are sending packets, and then here we have the IEEE 802.11, that is a wireless protocol, right? So then we have, this is the physical layer, right? So here on the receiver side we also have the IEEE 802.3 1000 base SX, right? So here we have IEEE 802.3. so this all is relevant to the lower layer. If we are taking two layers, then this is the data link, and here we have the physical. Then IP, so IP, this is the destination IP address, and here we have the again receiving the packets, and those packets are being sent to the TCP. Here we have performed segmentation, so here we are actually reassembling the data, and this reassembled data is sent to the application layer, and that application layer is using the HTTP protocol. You can say the browser, and the data will be. So this is the example, and then we have standardized protocol architectures, right? So for example, TCP/IP, OZ. So here we have, after having a lot of recap, now we are able to answer our question, what is a protocol architecture, right? So the software structure that implements the communication functions. Typically the protocol architecture consists of a layered set of protocols with one or more protocols at each layer. So there can be more than one protocol at one layer. So this is important because there can be different functionalities, because we have divided one task into subtasks, and those subtasks they can have different functionalities that has to be performed. For example, if we talk about the IP layer, so it is routing, and then the division of segments into packets, and so these are the two functionalities. So then it also have to make sure the error-free delivery of packets, right? So there are some mechanisms or protocols that are being used over the IP layer in order to accommodate that. So here we have our next review question. So what is a TCP/IP? So we will not discuss in details because we have a lot of discussion on TCP/IP. So you can see that here we have different protocols at different layers. So application layer we have FTP, Telnet, SMTP, and DNS. And transport we have two protocols, one is connectionless and other is connection oriented. IP layer, as I have mentioned, IP, and then we have sub protocols, OSPF, open shortest path first, and at the data link layer and physical layer we have some. So here is the example of a postal system. So this letter has to be dispatched somewhere in some other city. So you wrote the letter, you put it in an envelope, write down the address, and then put into the mailbox, and somebody pick the letter from your mailbox, and it is delivered to the central post office, and then from central post office it is sent to some other city, and then in that city the address is used, that is a header or control information, and the letter is delivered to the destination mailbox, and then from that mailbox letter is picked, and it can be read in order to retrieve the corresponding message. But in all that tasks, subtasks, there are further some functionalities that are involved, right? Sorting. So here you can see the person is sorting the letters accordingly, so it is putting the letters in the corresponding boxes, right? So within a post office, so that the person who has to deliver, he can pick the letters and then deliver. Or maybe this is the sorting for intercity delivery, right? So within a city, maybe there are different post offices, and they have a central post office. From central post office, they have to sort the letters so that they can be delivered to the corresponding post offices, right? So, and then this is the functionalities or tasks being performed. Central Post Office, New York, Central Post Office, Beijing. So there are a lot of there can be a lot of letters or packets. Local post office, and here we have another local post office, and there can be different means of communication. They can use air transportation. They can also use by road transportation, and the delivery can also be done by using bicycles. So this is so here we have the answer. Transmission Control Protocol, Internet Protocol are two protocols originally designed to provide low-level support for internetworking. The term is also used generically to refer to a more comprehensive collection of protocols developed by DARPANET and is used by ARPANET. So here we have to justify that what are the advantages of adopting the layered approach in the TCP/IP architecture. So first, we have mentioned that there are some applications that are using the common modules. So here is the stack, right? Benefits of layering. So of course, the complex task is chunked down into subtasks, and now we actually have reduced the complexity, and as a result we have to pay, so we have to handle more control information, and these are the headers which are being added at the each layer. So the burden of network application developer has been reduced. So if I'm a developer that has to develop application at the presentation layer, so I will be focusing on the presentation layer, and if somebody has to develop applications regarding the network programming or socket programming, so he will be focusing on the session layer. And if we go further, so if I'm a developer and I have to focus on the network layer, so or maybe I'm developing some hardware, some sort of module that has to function at the network layer, so I will be focusing on the network layer. So the burden of the application developer, and for me, for the hardware designer, has been reduced. So here we have the answer of following the layering decomposes the overall communication problem into a number of more manageable sub-problems, right? So router. So that is an important element whenever we talk about the communication by using a network, or maybe communication over the internet. So there is a very important device that actually performs routing. So there are different functions that it can perform. So actually the infrastructure of the internet is that we have different LANs, we have different WANs, or maybe different MANs, metropolitan area network, or maybe we have also some sort of wireless networks. So those all are interconnected. So you can say LAN is a smaller network, and then the WAN is a much bigger network, and MAN is in between WAN and LAN. So in order to have interconnection between those different networks, we can use a router, right? So we can also have interconnection of communication lines, and then of course its functionality. path determination and packet switching. So application, so we can also implement some sort of restrictions by using the router, and then we can also have some modules that can be plugged into the router in order to have a protocol conversion. For example, if one network LAN is supporting PPP, right, and the other network that is also a LAN, it is supporting HDLC. So and we have a router in between those different LANs, so they can communicate with each other. So it can also translate protocols. So then we have, when we talk about the router, so each network has its own addressing scheme. So it's the responsibility of the router that it can ensure, or it can make communication between two LANs that have different addressing schemes. Different scheme for assigning addresses to devices. For example, LAN uses 48-bit binary address for each attached device, and on the other side, the ATM network, it is using 15-digit decimal address. So if we have a router in between, so those different addressing schemes, they can be communicating with each other, right? So maximum packet size. So again, if we have different technologies, and those different technologies, they actually have capability of handling packet of different sizes. So it's the responsibility of the router that it can take bigger packet from one side and will be sending packets to the other side, smaller packets to the other side that have the capability of accepting packets of lower size, right? So segmentation and fragmentation. So here is an example. Maximum packet size of 1500 bytes, right? A maximum size of 100 bytes is common, right? So X.25, it can support only 1000 bytes, and the Ethernet can support 1500 bytes. So it has to be further segmented, and then this has to be done by the router. So here we have a router, ATM, and then we have IEEE 802 technology on the other side. So different packet size, different addressing scheme. So the router can accommodate all, and then it can make possible that the two networks, right, ATM network and this wireless network, they are communicating with each other. So here we have the scenario regarding the sender, so application layer, right, preparing the data, and then we have the TCP layer segmentation. Then TCP segment will segment the data, and then duplicating the segments, right? So here we have the operation of the TCP IP, actions that are being performed at the router, arrive at the router, data is arrived at the router. So process the cell. One side we have the ATM, and on the other side we have the different technology, routing the packet, forming the LLC PDU, protocol data unit, framing, right, and then transmission. So here are the components of the router: hardware component, network interface. Of course, it should have hardware interfaces in order to receive the data from different technologies. For example, Ethernet, maybe ATM, or some routers, they also have the fiber termination support. So then PC router, and then we can also convert a simple PC into a router if I have more than one network card on a router. So we can one interface can be connected to one network, one segment, and the other interface can be connected to the other network. Then we have also commercial routers, for example, routers from different companies, Cisco, Juniper, and so on and so forth. So these functional components, we have a router functionality, routing table, that is important, and then we have the forwarding. So here this is the control path and this is the data path. So it means forwarding is related to the data path, and we have the routing protocol and then routing table update, right? So control and data path. Include route calculation, because of, if we have more than one choice in order to route a packet, so we can calculate the overheads, and then maintenance of the routing table, because if there is a new route or there is some route that is disconnected, so we have to update the routing table, and then we have to execute the routing protocols, forwarding, high-end commercial routers, right? And here we have the architecture: routing table, routing decision, right? Routing table, routing decision, and this is the switch fabric, and here we have the queuing, scheduling. These are the components, so we will not go into details, right? And these are the operations that are being performed. So actually it is a layer 3 device if we talk about the OZ layer, and that is physical, data link, and network. So router operates at network layer, so it accepts protocol data units on incoming network, examines the PDU, and then makes decisions for the next hop, right? Can also modify PDU. Okay, so here we have the answer. A router is a device that operates at the network layer of the OZ model, and it connects dissimilar networks. So it means that if we have a network that is actually running on the Ethernet technology, and on the other side we have another network that is running on the ADM technology, so those two networks, they are using different technologies and they are called dissimilar networks. So if we have a router in between, so they can communicate. So there is one condition, that the router should have the interface in order to connect those different dissimilar networks. So here we have the summary for today's lecture. So today we talked about protocol, a protocol stack, what is a protocol stack, and how we will be handling a protocol data unit. And then we talked about the protocol architecture and how we can define the protocol architecture and why the protocol architecture is important for us. And then we talked about the stack. Actually TCP/IP is a protocol stack. It's each layer has one or more than one protocol that is actually defined in order to perform the functionality over the corresponding layer. And then we also discussed about the advantages of adopting the layered approach and what we have to pay in order to have the layering approach. We have to handle the control information because every layer is adding its own header. So if we talk about the sender, so the sender, the layers that are actually being used from the sender perspective, they are adding control information or headers from the sender perspective, and those control information is being used or exploited at the receiver, or maybe they are also being used by the intermediate devices, for example networks, routers, switches, and some other devices. So this is the extra, but as a result we have a huge benefit of dividing the complicated task of communication into subtasks, and you can have a lot of further advantages, that if somebody has to develop the application at the presentation layer, or maybe the application layer, or maybe the transport layer, so they will be focusing on the corresponding layer. And if somebody has to design a hardware for a particular layer, so they know the pros and cons of, or they know the limitations they are going to have, so they will be focusing. So we also have a very huge advantage that if we have some changes that has to be done at a certain level, certain layer, so we know our restrictions, our boundaries, so those changes will not affect the functionality at the other layer. So there are a lot of different advantages. And then finally we talked about the router. That is an important element when we talk about the communication between devices. So if we have different technologies and those different technologies are being deployed over two different LANs, one side we have Ethernet and on the other side we have the ATM. So there are different packet sizes, different technologies and different mechanisms that are being used in order to have communication between those LANs. But if they want to communicate with each other, one LAN is want to communicate with the other LAN, so we can use a router. So we also discussed the functionalities and operations that are being performed by the router. So that's all for today's lecture. So मेरी तरफ से अल्लाह हाफिज़, अपना ख्याल रखिएगा, अस्सलाम वालेकुम.